We present RigNeRF, a fully controllable neural model for 3D portraits. This is joint work between Stony Brook University and Adobe Research. Given a training video with a variety of facial expressions, head pose, and viewing direction, and the corresponding 3D parameters, we aim to build a radiance field that models the whole 3D scene with full control over facial expressions, head pose, and viewing directions of the scene. Prior work, such as the deformable NeRFs proposed in NeRFees and HyperNeRF, are able to reconstruct the deformations in the training data and allow novel view synthesis. However, they do not offer any control over facial expressions or head pose. On the flip side, NeRFace, while allowing control over facial expressions and head pose, does not model the full 3D scene. Thus, novel view synthesis is not possible. In contrast to prior work, RigNeRF enables head pose and facial expression control, novel view synthesis, and reanimation with full control over head pose, facial expressions, and viewing direction. So how does RigNeRF work? Given a frame in the deformed space, as in a standard NeRF, we shoot rays and sample points on them. These points are then transformed to the canonical space using a deformation field. This deformation field is the sum of a coarse 3D-based deformation field and a fine deformation field predicted by an MLP that corrects the coarse field. Once in the canonical space, the points on each ray are rendered using standard volume rendering. We now visualize the deformation field that maps 3D points from the deformed space to the canonical space. The canonical space is defined as the space where the 3D has zero head pose and a neutral facial expression. First, we calculate the transformation of the 3D vertices to the canonical space by subtracting their deformed coordinates from their canonical coordinates. This 3D deformation is then projected to the 3D points by first calculating the closest 3D vertex to each 3D point. The deformation at the 3D point is then equal to the deformation of the closest vertex, weighed by the inverse of the distance between the vertex and the 3D point. Since the 3D only approximates the shape of the human head, the deformation given by it is coarse and inaccurate. To fix this, we use a deformation MLP to correct the coarse estimate of the 3D deformation, giving us the final deformation field. Once trained, RigNeRF can be controlled using 3D expression and pose parameters. These parameters can be derived from a driving video, be input manually, or can be obtained from any other source. We now show comparisons with baselines. Using the driving video, we reanimate RigNeRF, HyperNeRF with expression and head pose controls, which is denoted as HyperNeRF plus E/P, and NeRFace in a constant view. As can be seen, the reanimation results of RigNeRF have significantly higher fidelity to the facial expressions and head movements of the driving video compared to the two other methods. We now show results of control using expression and pose parameters from a 3D